earlier classes, you have learned about the area of a square, and that is side A into A, right? Right. So, square of a number can be seen in a similar way. So, if a square of a number is the product of the number with itself. So, for example, if we want to take the square of 4, then 4 into 4, that's a number multiplied by itself, is equal to 16. And that's the square of 4. Similarly, for 9 square, we have 9 into 9, and that is equal to 81. Right? We can also have that for any different kind of rational number. Say 2 by 5. What's the square of it? 2 into 2 divided by 5 into 5. That comes out to be 4 by 25. Right? So basically, squares of natural numbers are called square numbers or perfect squares. And these can range for, say, for like 1 to 100, 200. There are a couple number of perfect squares. And these are 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. Right? So we need to understand that all natural numbers are not perfect squares. So just to jog down your memory, in general, if a natural number m can be expressed as n square, where n is also a natural number, then m is a square number or a perfect square, right? Let's consider a simple number as 16. How do we know whether 16 is a perfect square? In order to do this, we will need to do some prime factorization. We have already learned that in our previous classes. So I will not go into that, and I will just create a very simple. So we have 16 and 2, 8, and 2 again, and 2 again. That's how we have. So 16 can be written as 2 into 2 into 2 into 2. So we have 4 2's. And now then we have to create pairs of these equal prime factors. So these are 2 into 2 and again 2 into 2. So that's how we know that this is a perfect square. Let's take another example of a bigger number, say 144, and we'll do the prime factorization. So let's do that. 144, we have 2 again, 72, 2 again, 36, 2 again, 18, 2 again, we have 9, get 3, 3, 3, then 1. So 144 can be written in prime factorization form as 2 into 2 into 2 into 2 into 3 into 3. So let's make the pairs 2 into 2, 2 into 2, and 3 into 3. So we know that this is a perfect square. Now let's do some kind of a example that might come in the exam. Okay, so let's take a big number. So is 152 a perfect square? So what's the first step? We'll do the prime factorization. 152 into 2 is 576, and 2 again, we have 288, and 2 again, we have 144, 2 again, we go to 72, 36, 18, 9, 3, and 3 again. So 1152 can be written as 2 into 2 into 2 into 2 into 2 into 2 into 3 into 3. So we'll make the pairs 2 into 2, 2 into 2, 2 into 2. There's 1, 2 left, and 3 into 2. So as there's one number that is left, So 2 is not paired up. So this is not a perfect square. So the answer for this question would be no in our exam, right? So another kind of question that we get in our exams is that sometimes they already tell us that the number given is not a perfect square, and what number should be multiplied to that number to make it a perfect square. So how do we address this kind of a problem? So first we'll do the basic prime factorization that we do in every question. So we have 720. We do prime factorization, we get 360, then 180, then 90, then 45, and then we have 15, 5, 5 again. So here we will again write 720 in the prime factorization form, that is 2 into 2 into 2 into 2 into 3 into 3 into 5. So let's make the pairs. And here we see that 5 is unpaired. And therefore, if we multiply 5 to 720, then we will get a number that is a perfect square, because then then we will be able to make a pair of 5. So therefore, the smallest number, so in our answer we would write smallest number that should be multiplied needs to be multiplied to 720 to make it a perfect square is 5. And sometimes they ask you what would be the perfect square. So you would say the perfect square would be 720 into 5. And that value comes out to be 3600. So here we have a question where we need to find the smallest number that we divided from this value 2527 to get to make it a perfect square. So we follow the same pattern of finding the prime factorization of the number 2527. And here we get 7, which can come out to be 361, and then we get 19, 19, and that comes out to be 1 again. So our prime factorization of 2527 is 7 into 19 into 19. So here 19 makes a pair, but 7 is unpaired. So in this type of question, when you need to divide something, so we need to divide 7 by 2527 to get that perfect square. To make 2527 a perfect square, we need to divide 7 from it. And that's how we do it. So square numbers are quite special as compared to other natural numbers, and therefore there are certain properties that they possess that it does not exist for any other kind of natural number. So let's look at these properties, and you will find it quite amusing to see how special these numbers are. So where the first property is a number which has 2, 3, 7, or 8 at its unit place is never a square number. So we need to understand, let's go back a few steps and see the 1 to 100 perfect squares here. So we have 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100. So our first property says that if the number has 2, 3, 7, or 8 in its unit place, that is not a square, that is never a square number, and that is evident from our 1 to 100 perfect squares, right? So that's our first one. So the type of questions that does come with these kinds of properties is that we need to tell whether a number is a square or not. So say whether 2037 is a perfect square. So using the property above, We know that the unit place is 7. So as unit place is 7, this is not a perfect square. So that's how we tackle questions like this. Moving on. So a very interesting next property is that if there is a number that is ending with odd number of zeros, that number will never be a perfect square. Let's take these examples of a few numbers. So let's say 10 square. What is it? 100, right? 20 square is 400. So we have two zeros here, right? And then what is 100 square? That is 10,000 with four zeros behind it. And 200 square is 40,000 with four zeros behind it. So a square is always going to be one with the even number of zeros behind it. But there are also some numbers which does not have which have even number of zeros, but it's still not a perfect square. Examples of those can be, say, 300 or 60,000 and many more. Right? So it's not, conversely, it's not true. So we need to be mindful of what it is telling us. So our third property is squares of even natural numbers are even and squares of odd natural numbers are odd. So it's very easy to understand this. So let's take a very quick example of 4. 4 square is 16 and 16 is an even number. We have 8. 8 square is 64, which is again an even number. And if we go to odd numbers, 3 square is 9, 9 square is 81, and both these numbers are odd numbers. So that's how the thing goes. And that's a very useful property to know. Just a very basic thing, but it's good to know. Unit place of any natural number, then the square of the unit place would be unit place of the squares would be 1. So for this we can have for this we can have 1, this we can have 81, and this goes on for everyone. For 4 we have 16, and 6 we have 36. For 2 we have 4, and for 8 we have 64. For 3 we have 9, 7, 49. 5 we have 25, 0, that is 0. So that's how it goes, and it can be for anything, any number with the unit place as these numbers. Next up, we are going to talk about some interesting number patterns that come as we talk about squares and square and the natural numbers. So let's first look at numbers between consecutive square numbers. So we'll first observe something. So let's observe the following numbers. So we have 1, which is again 1 square, can be written as that. Then we have numbers between that as 2, 3, and then again comes 4, which is again 2 square. So similarly, we have 5, 6, 7, 8, and then again comes 9, which is again 3 square. So what we are trying to say is that let's see if there is 2 square minus 1 square, that comes out to be 4 minus 1 equal to 3. And the number between 2 square and 1 square, that is 4 and 1, is 2 and 3, which is 1 less. This is 1 less than this number 3. So this is a very simple observation. Similarly, if we look at 3 square minus 2 square, that is 9 minus 4, we get 5. And the number between 3 square and 2 square, that is 4 and 9, we have uh, 5, 6, 7, and 8. And this is 1 less than 5. So this is whole is 4, and this is 1 less than 5. So this is a very simple observation that we have about these numbers. So we come to a point where it means that there are 2n non-square numbers, that is 5, 6, 7, 8, between the squares of two consecutive number n and n plus 1, that is 2 and 3. So this was our first observation. So a question that can come out of this is what are the natural numbers that lie between and 9 square and 10 square? A question that can come out from this could be how many natural numbers lie between 9 square and 10 square? And for this we can apply the statement above, where we have 9 square plus, where we have 9 square and 9 plus 1 whole square, and therefore n is equal to 9. And from the statement above we have the number of natural numbers as 2n, which is equal to 2 into 9 or 18. The second interesting property is on the addition of odd numbers. So let's observe the following. So here we see that 1 is just the natural number and it is equal to 1 square. 1 plus 3 again comes out to be 4, which is 2 square. 1 plus 3 plus 5 is 9, and that is 3 square. And for again, moving on, we have 1 plus 3 plus 5 plus 7, that is 16, and that is 4 square. So this comes out to be a very interesting pattern where we observe that the sum of the first n odd numbers is n square. So a very simple example that comes out of this is find whether a number is a perfect square or not. So let's take the example of 81. And for this, what we need to do is first we need to successively subtract numbers, the odd numbers 1, 3, 5, 7, and so on until and unless we get 0. If we get a negative number, then that number is not a perfect square. So let's do this through this example. So first is 81 minus 1, that is 80. Then we have 80 minus 3 equal to 77. 77 minus 5, which is equal to 72. 72 minus 7, which is equal to 65. 65 minus 9, which is equal to 56. 56 minus 11, which is equal to 45. 45 minus 13, which is equal to 32. 32 minus 15, which is equal to 17. And 17 minus 17, which is equal to 0. So as we have reached the 0 number, that means that 81 is a perfect square. And that is a square of 9. Moving on, let's look at the third interesting pattern on these numbers. So we'll observe the square of odd numbers as a sum of consecutive numbers. So let's see. 3 square is 9. It can also be expressed as 4 plus 5. Right? We can also find this out as 4 is equal to 3 square minus 1 by 2. And 5 is equal to 3 square plus 1. That's how it comes out. So even for 5 square, we have 25, which can be expressed as 12 plus 13. And similarly, we can go for 11 square, which comes out to be 121, 60 plus 61. So that's a very interesting thing to note. So a very simple question that can come in the exam based on this is that express this square as a sum of two consecutive integer. And let's take the example of say 29. 29 square. So how do we find this? So as mentioned here, we'll take again the same method, and the first number will be calculated as 29 square minus 1 by 2. This comes out to be 841 minus 1 by 2 equal to 840 divided by 2, which comes out to be 420. And the second number is 29 square plus 1 whole by 2. And this comes out to be 421. So the two numbers are 420 and 421. We can also see as the 841 is equal to 420 plus 421. That's how we can get to that. So let's observe 25. This can be 25 square can be written as 625, which can also be written as this number 6, which is 2 into 3, 100, hundreds plus 25. We can also write this for 35 square. So the 35 square is equal to 1225, where this 1 2 can be written as 3 1 2 or 12, it can be written as 3 into 4, hundreds plus 25. So this gives us a very simple formula which can be used for any kind of square with unit digit 5, and that formula is, so we'll take a and 5 whole square. Here a can be anything from 2, 3 and so on, and then we have 5. So this whole number would become 25, 35, etc. So a5 square can be written as a, that is 2, and then plus into a plus 1, which is 2 into 3, hundreds, and then we add 25 to it. So this is a quick formula to find that out. So next up we have Pythagorean triplets. This is a very interesting property, and this relates to the Pythagoras theorem we have already studied in our previous classes. So let's observe this very simple example first. So say we have 3 square plus 4 square is equal to 5 square, right? We know that we can also simplify it to understand. So 3 square is 9 plus 16 is equal to 25, right? We can also use it as 6 square plus 8 square, which is equal to 36 plus 64 is equal to 100, or 10 square. So the Pythagorean triplets are 3, 4 and 5, and then 6, 8 and 10. So, and there are many more Pythagorean triplets like this. There's a simple formula to know whether a natural number comes within a Pythagorean triplet, or a Pythagorean triplet exists around that number. If we have three natural numbers m, n, and p, they said to form a Pythagorean theorem, a Pythagorean triplet m, n, p, if m square plus n square is equal to p square. We have already understood this through the example before. But if we want to write this m and p in the same form, where m is one of the numbers, then we can write it in the formula which you will need to remember for your exam. So which would be 2m comma m square minus 1 and comma m square plus 1. So these three numbers with m as the single same natural number would form the Pythagorean triplet. And the type of questions that will come from this would be, a question that might come is, write a Pythagorean triplet whose smallest number is 8. So let's take, we know that the Pythagorean triplet are 2m, m square minus 1 and m square plus 1. So let us first assume that m square minus 1 is 8, and then we will solve this to get m is equal to 3. And as we have this as a natural number, m equal to 3, we can find the other pairs in other values in the Pythagorean triplet, and these would be 2m, which can be written as 2 into 3, 6, and m square plus 1, that is 3 square plus 1, and that is 10. So this triplet comes out to be 8, 6, and 10. But here 8 is not the smallest. right? So we'll try again, and let's assume another value is 8. So let's assume 2m is equal to 8. And then we get m is equal to 4. Then we'll again solve for others. So m square minus 1 would be 4 square minus 1, that is 15. And m square plus 1, that is 4 square plus 1, that is 17. So the Pythagorean triplet here would be 8, 15, and 17. And that's how we find the Pythagorean triplet using this formula. And that's all for today. Thanks for watching. See you next time.